On April 26, 1986, the world witnessed the most catastrophic nuclear disaster in history. The Chernobyl nuclear power plant, once a symbol of Soviet technological prowess, became a name synonymous with devastation. But what many don't realize is that this disaster wasn't caused by a sudden, unpredictable failure. Instead, it was the direct result of a planned safety test. A test that, through a combination of design flaws and human error, went horribly, tragically wrong. Today, we're going to peel back the layers of that fateful night and understand how a routine electrical test turned into a recipe for disaster. The story begins not with an explosion, but with a simple question of safety. What would happen if the power plant lost all external electricity? This was a critical concern. The massive water pumps that cooled the reactor's core needed a constant supply of power. Without it, the core could overheat and melt down. The plant had backup diesel generators, but they took about a minute to kick in. That 1 minute gap was the problem. A minute without cooling was a minute too long. So the engineers at Chernobyl devised a clever plan. They theorized that the momentum of a spinning down steam turbine could generate enough residual electricity to power the immense cooling pumps during that crucial 60-second gap, bridging the time until the diesel generators took over. It was a sound idea in principle. This procedure had been attempted before at Chernobyl and other similar plants, but it had never been successfully completed. On the night of April 25, 1986, the crew of reactor number 4 was scheduled to try again. The test was supposed to begin during the day shift, with a team that was well prepared and understood the procedure. But things started to go wrong almost immediately. An unexpected power demand from the regional grid controller in Kyiv meant the test had to be postponed. The reactor, which had already begun its power-down sequence, was forced to stay online for another 9 hours. This delay was the first critical link in a chain of catastrophic events. By the time the grid controller finally gave the green light to proceed, it was past midnight. The experienced day shift had gone home, replaced by the night crew. This new team was less experienced, less prepared for this specific non-routine test, and they were already tired from a long day. They were essentially handed a complex and potentially dangerous experiment with minimal preparation. To conduct the test, the reactor's power level needed to be reduced significantly. From its normal operating level of 3,200 megawatts thermal down to about 700 to 1,000 megawatts. As the night crew took over and began to lower the power, a critical operational mistake was made. The power level dipped far too low, plummeting to just 30 megawatts, essentially bringing the reactor to a near halt. This was a hugely dangerous state. At such low power, a phenomenon known as xenon poisoning began to take hold. Xenon-135 is a byproduct of nuclear fission, and it's a powerful neutron absorber. Think of it like a sponge that soaks up the neutrons needed to sustain a chain reaction. Under normal operation, the xenon is burned off as quickly as it's created. But at low power, it builds up rapidly, making it incredibly difficult to increase the reactor's power again. The reactor was becoming unstable. Faced with a stalled reactor and under pressure to complete the test, the operators made another fateful decision. To counteract the xenon poisoning and raise the power, they began pulling out the control rods. Control rods are the reactor's primary safety and control mechanism. Made of neutron-absorbing material like boron, they're inserted into the core to slow down the reaction and withdrawn to speed it up. Regulations stipulated that a minimum of 28 control rods must remain in the core at all times to ensure a rapid shutdown was possible if needed. But in their desperate attempt to get the power back up to the required level for the test, the operators overrode safety systems and withdrew almost all of them, leaving only about 6 or 7 rods in the core. They were essentially driving the reactor with the emergency brake almost completely disengaged. The reactor was now a ticking time bomb, but they didn't know it yet. They managed to stabilize the power at around 200 megawatts, still far below the planned level for the test. But they decided to proceed anyway. It was now 1:23 a.m. on April 26. The test officially began. The operator shut off the steam to the turbine, simulating a total power blackout. The turbine began to coast down on its own momentum, and as planned, it started generating some electricity for the water pumps. The initial part of the test was actually working. But here's where the second major problem, a fatal design flaw in the RBMK reactor itself, came into play. As the turbine-powered pumps slowed down, the flow of cooling water through the core decreased. In most reactors, this would slow the reaction. But the RBMK had what's called a positive void coefficient. This means that as the water, which also absorbs some neutrons, turned into steam bubbles or voids, the nuclear reaction didn't slow down, it sped up. More steam meant more reactivity. Within seconds, a power surge began in the core. The decrease in cooling water created more steam, which in turn caused the reactor's power to rise, which created even more steam, starting a terrifying feedback loop. Alarmed by the sudden power spike, the operator hit the AZ5 button, the emergency shutdown switch designed to scram the reactor by fully inserting all the control rods back into the core. This action should have saved them. Instead, it triggered the explosion. And this was because of the RBMK reactor's most damning secret. The tips of the control rods were not made of neutron-absorbing boron, but of graphite. Graphite is a neutron moderator. It actually increases reactivity. The designers did this to displace water when the rods were fully withdrawn, improving efficiency. So, for the first few seconds of the emergency shutdown, as the rods began to re-enter the core, the graphite tips displaced the water and caused an instantaneous, massive power spike in the bottom of the reactor. The power output skyrocketed to an estimated 100 times its normal level in just a fraction of a second. The immense energy release flash boiled all the remaining water, creating a colossal steam explosion that blew the 2,000-ton lid clean off the reactor vessel. Seconds later, a second. More powerful explosion, likely a hydrogen explosion from the reaction of steam and zirconium, tore the building apart, ejecting superheated radioactive graphite and nuclear fuel into the open air. The core was exposed, burning and spewing a plume of deadly radiation into the atmosphere that would drift across Europe. The Chernobyl disaster was not an accident in the sense of a random, unpredictable event. It was the predictable outcome of a flawed design, operated outside of its safety margins by a crew under pressure. The desire to complete a safety test led them to violate their own safety procedures, pushing a fundamentally unstable machine into a state where it was impossible to control. The delayed test, the inexperienced crew, the desperate push to raise power, the violation of control rod limits, and finally, the fatal flaw in the shutdown system itself, which was a step on the path to ruin. It's a sobering lesson in how complex systems can fail, and a powerful reminder that safety protocols in a culture of safety are not just bureaucratic rules, but the last line of defense against catastrophe. Thanks for watching. If you found this breakdown interesting, be sure to like and subscribe for more deep dives into the stories that shaped our world.